This is my AI voice assistant.
Hey Plato, what time is it?
7:16 p.m.
Hey Tomato. Hey Plato, what's the weather?
Right now it's overcast and 53 degrees, with a low today of 44 and a high of 56.
It's running on a Raspberry Pi 4 with 4 gigabytes of memory, and while it's running in the background, it only uses about 5% of the CPU and less than 2% of the RAM. While designing it, I came across a lot of very simplistic examples of DIY AI voice assistants. Many of them rely on constantly streaming audio to Google or some other third party in order to convert the audio to text, so that the voice assistant code can then check if the wake word is in that text. I wanted to avoid this for 2 reasons. First, and less importantly, that'll end up using a lot of network to constantly stream all the sound from your microphone. Second, I didn't want to constantly stream all the sound from my room over the internet to a third party. On the other hand, if I made everything myself, I'd have to make an audio AI that would be able to understand every word in the English language. I settled on a happy in-between. I made a neural network that will run locally on the device to detect a wake word. Once it detects a wake word, it will use an internet-based text-to-speech system to determine the command. That way, I'm only sending the audio for a command over the network, and I know exactly when it's listening to me. After that, it's as simple as parsing the text and then executing whatever code corresponds to that command. This video is going to be all about the design of the system, the choices I made along the way, and the theory behind how everything works. There'll be another video going into the details of how everything is implemented in code. Going into this project, I already had a pretty decent background of machine learning in the context of computer vision and natural language processing, but no experience using machine learning with audio. At its core, this video is going to be about how to take basic knowledge about machine learning and neural networks and apply it to audio. After some trial and error, I ended up using a CNN implemented using TensorFlow. If you want more background information about generally how neural networks work, or particularly CNNs, I would recommend learning about them in the context of computer vision, because I think it's a bit easier to visualize how they work. I'm going to move quickly through this first part, but I want to start with the big picture. So my first question, what is sound? Everyone generally knows it's a wave that travels through the air. Instead of moving air particles up and down, it's actually compressing them together and then moving them apart. So sound is just really fast changing in air pressure. And that brings us to how microphones work. Microphones are really just air pressure sensors. They take recordings of the air pressure at regular intervals. Usually this interval is about 44,000 times a second, or 44 kilohertz. That's what a sound file is on your computer. It's the list of samples recorded by the microphone, along with other metadata like the sampling rate. Okay, so now we know how computers store sound, and one potential idea for building a machine learning model would be to just take these air pressure samples that your computer has and feed it directly into some type of neural network. This isn't a terrible idea, and it does work, but other methods of transforming audio information for neural networks have been shown to work a bit better. The data that we put into neural networks is called features, because it should be representative features of whatever our input is. Like if you were describing someone's facial features to an artist, you probably wouldn't tell them exactly where to draw lines or to shade. You'd tell them the shape of their mouth and the haircut they had. With features for a neural network, you want to use the simplest data that does a good job of distinguishing one input from another. One way we can get important information from a waveform is with the Fourier transform. Here I've made 3 separate tones. Then we can combine those separate tones together to make a chord. If we perform the Fourier transform on each of the tones and then lay them over each other, we can see that it had pulled out the frequency of each tone. Then, if we perform the Fourier transform on the entire chord, we can also see that it pulled out all of the individual tones. To see how a Fourier transform could be a bit more helpful than a raw waveform, think about trying to differentiate a tiger roaring from a mouse squeaking. It would be difficult to tell the difference just by looking at the waveform, but it would be super easy to tell the difference looking at a Fourier transform. The downside of the Fourier transform is that it throws away all the time data. It's just the pitches that exist in the recording without any sense of when those sounds happen. Now we're going to use the same 3 tones, but play them one after the other. Even though these are clearly different, the Fourier transforms look exactly the same because it's the same frequencies. On the other hand, when we create spectrograms, we can easily see the difference between these sounds. We can make another sound that ends with a chord so that we can see all three frequencies within the spectrogram. A spectrogram takes the idea of a Fourier transform, but includes more information about when the different sounds happen. To make a spectrogram, you break the audio up into windows, then calculate the Fourier transform for each window. You can also change the hop size, which is how far the window moves each time you recalculate the Fourier transform, to control how much resolution the spectrogram has in terms of time. Changing directions a bit, there's something else that can help us out called the Mel scale. Human ears actually don't interpret sound exactly corresponding to the frequency of that sound. Humans are better at differentiating low frequency sounds and not very good at differentiating high frequency sounds. Human speech is relatively low pitched compared to a lot of other sounds in our lives, so the Mel scale does a good job of pulling human speech out of audio. Finally, we're going to end up combining the spectrograms and the Mel scale to get the features for our neural network. This is called Mel Frequency Cepstral Coefficients, otherwise known as MFCCs. I'm not going to do a deep dive of how to calculate MFCCs exactly, but it is effectively a combination of a spectrogram and using the Mel scale. What we're going to do is create a spectrogram, so split the audio up into windows, performing a Fourier transform on each window to get the frequencies. Then we convert the spectrogram using the Mel scale. Then we do some more stuff that I'm not going to get into. It's not that it's that complicated, and the Wikipedia page talks about it, but it just doesn't really matter for our purposes. Then ultimately, you end up with the data that you're putting into our neural network. We can also reorder the steps we just said to think about in terms of calculating the MFCC for a single window. The way you do this is you take a window of audio, get the Mel frequency cepstral coefficients for that window, move the next window by the hop size, rinse and repeat. Something else that we might want to know before we go forward is the shape of the matrix that we're plugging into our neural network. I already talked about two of these parameters, window size and hop size. Window size is how much audio is going into a single MFCC calculation, and hop size is how far we move the window each time we calculate the MFCCs. There's two more parameters involved in how much data we can put into the model at once. The first is number MFCC. This is how much resolution each MFCC calculation should have. This is actually going to be a relatively small number. For our purposes, it's just 13. That means each time we calculate the MFCCs for a window of audio, we're going to get 13 numbers spit out. The second one is number features. This is just how many separate MFCC calculations are going to be put into the neural network as a single input. I'll explain this a bit more in a minute, but we want this parameter to be big enough that when we say the wake word, it fits into a single input to the model. It won't work if the model only gets to hear part of the wake word. Okay, great. So that's everything about how we're going to convert the audio that our microphone is picking up into what we're putting into the model. We're ready to talk about how to get the data to train our model. We're going to need audio samples of the wake word and plenty of audio samples of noises that aren't the wake word. This is most likely going to involve a combination of you recording yourself saying the wake word, recording yourself saying other words, or making noises around your room, and potentially even downloading audio from the internet. If we want our model to work well, we really want a good data set of your voice saying the wake word and other words that aren't the wake word, all using the microphone that you'll ultimately use for your voice assistant. We don't want to spend all day recording ourselves saying the same wake word over and over, so we're going to use a trick called data augmentation. I only ended up creating around 100 real recordings of positive samples to train my model, then multiplying those using data augmentation. Data augmentation is the general practice in machine learning of artificially creating new data from existing data. It's basically copying and pasting data while changing it slightly so that the models are able to learn a little bit more each time. Just to understand a little bit more how data augmentation works, imagine you're making a computer vision model to differentiate dogs and cats. You should take a picture of a dog, resize it, recolor it, recrop it, or even flip it, and your neural network should still identify it as a dog. Now you can apply those 4 different augmentations to your entire dataset, and all of a sudden you have 5 times as much labeled training data as you started with. We're going to do the same thing, but to audio files. First, let's talk about augmenting the plain audio, otherwise known as waveform augmentation. These are going to be ways to change the audio slightly while still sounding like the same words. The first is changing speed. This is exactly what it sounds like. We're going to either speed up or slow down the audio a tiny bit. Changing pitch. This is also exactly what it sounds like. We're either going to pitch the audio up or down. Shifting time. This basically means adding silence at one end of the noise and then removing silence from the other end. We want to avoid significantly cutting off any words in the sample. Noise injection. This means adding background noise under the audio sample. You could go and find different background noises and lay them over the sample, but I'm just going to end up using white noise. Finally, there's one more waveform augmentation that we could think about using, but we're not going to end up using it in this project. That's changing the volume. This might be helpful if we were plugging our waveforms directly into a neural network, but the MFCC calculation doesn't really depend on the volume of the noise. There's one more form of data augmentation that I end up using in this project, and it actually happens after we calculate the MFCC values for our samples. It's based on a research paper called Spec Augment, and it basically is just going to hide a small amount of the data from our model so that during training, our model doesn't become too dependent on any single part of the features. Okay, so at this point, we know everything we need to do to create all of the training data. Let's talk about what the neural network is going to look like. I'm not going to talk all about how a neural network works or the theory behind training a neural network. I'm just going to talk at a high level about the different general types of neural networks you can build and why I ended up using the type that I did. Generally, when you're working on stuff like this, it's best to just take a neural network architecture that someone else has already come up with and seems to work well, and just make slight adjustments for whatever you're trying to do. A lot of success with neural networks is just kind of empirical, what seems to work best. There's no need to reinvent the wheel here. So my first idea for the type of model to use was something that has some sort of context. Obviously, when humans are listening to speech, we can remember what was already said in the sentence, if you're a good listener. So I thought this might be helpful for what I was building. A kind of neural network model that already has this kind of context is called a recurrent neural network, or RNN. Basically, each time the RNN processes data, it spits out two things: an output, so its prediction, and then data representing the context of everything it's processed. Each time the RNN needs to process something new, you stick in the sample you wanted to process, and then the context from the previous step. I actually ended up building this entire wake word system with a type of recurrent neural network, specifically implementing it with a gated recurrent unit, or GRU. Here's why I didn't end up using that. RNNs are more difficult to train and take more resources than other types of neural networks that don't have context. For an example of why that's the case, let's say you're building a model to figure out what words are verbs. If you're using an RNN while you're training, you have to process the whole sentence, then go back through all the calculations that happened for each word over the course of the entire sentence to figure out how you need to update your model to perform better. If you're using some type of model without context, you can process each word simultaneously in parallel without having to worry about the words that came before. This speeds up training a lot, especially when you're using a GPU, where you can do a lot of things in batch or in parallel. Another, frankly larger reason that I ended up switching to a different neural network model is that I couldn't get the GRU model that I was using to be supported by TensorFlow Lite. In case you don't know what TensorFlow Lite is, it's not really important, and I'll get to that more later, but it's basically just how we're going to end up optimizing our model to run on a Raspberry Pi, which doesn't have a ton of computation power. So, after building everything with an RNN-based model and realizing that it wasn't the best way to do things, I ended up switching to a convolutional neural network, or CNN. If you have any knowledge of computer vision models, you've probably heard of a CNN. It's typically used in computer vision because it's a type of model that basically breaks up a picture into little sections to get more information about parts of the image. This type of model doesn't have the same sense of context that an RNN has, but as the wake word phrase can fit into a single input to the model, we shouldn't need any context. In the system I built, we end up putting 1.5 seconds of audio into the model for each prediction, which should be plenty of time for a wake word. In practice, this has just as good, if not better, prediction accuracy, trains much faster because there's no context, so more calculations can be done in parallel, and the model ends up being much smaller and faster, especially after we optimize it with TensorFlow Lite. Before I finish talking about the theory behind the system, I want to quickly talk about the difference between the model's prediction and what we're actually going to consider a wake activation. Based on the input, the model is going to output a value between 0 and 1, where 1 means that the model thinks it heard the wake word and 0 means that it thinks it heard something else. We're only going to consider a prediction of greater than 0.7 as being an activation for the given input. Then, we're only going to wake if around 3 consecutive inputs result in an activation. This is because the wake word will be smaller than one input to the model, so if we actually said the wake word, then the model should output multiple activations in quick succession. So here's the entire summary about how the system's going to work. The whole time the wake word engine is running, we're going to keep track of the feature matrix, which is just the MFCC that are put into the model. We're going to start with this being all zeros, as if there was silence leading up to starting the engine. Then, this is what the loop is going to look like for the engine. This is what we're repeating over and over while we're listening for the wake word. First, we read some bytes of audio from the microphone. Then we calculate the MFCC features from that audio. We'll also want to save the bytes of audio that we'll need for the next iteration of the loop. Then we add the new MFCC features that we just calculated into the feature matrix that we're keeping track of to input into our model, removing the oldest MFCC features so that the matrix stays the same size. Then we'll pass those features into the neural network and get out a prediction. This is going to be a floating point number between 0 and 1. Finally, we compare that prediction to other predictions to figure out if this should count as a wake. Then we repeat the process. Each time we get new MFCC values, we push back all of the values in the feature matrix. So we delete the oldest values and put the new values in at the end. All right, so that's all the theory behind my design. I didn't talk much about how we process commands, but that's pretty straightforward. Once we get the wake signal, we just use some third-party text-to-speech to figure out what was said in the command, parse the text, then run whatever code corresponds to the command. At the beginning of the video, you could see that I already set up commands to tell me the time and the weather. I plan to implement more commands soon, but that should be easy compared to everything else. I'll just need to write a Python script for whatever the command should do. There will be another video where I go in depth about how I coded this and talk some more about the details of the implementation. Thanks for watching.